In this section, we're going to review a topic first that you probably have already experienced in trigonometry, but it's always good to review these topics before we expand upon them. And the topic at hand are parametric equations. So up to this point, we've really only worked with functions. Functions are a type of relation that passes a vertical line test, or more precisely, we could say, in general, for every item that exists in the domain of a function, that item corresponds to exactly one item in the range of the function. And if we're talking about points on a number scale for the x-axis and the y-axis, it works out to a graph that passes a vertical line test. But that's very limiting in the types of analysis that we're actually able to do here, because, for instance, let's say we want to work with the calculus of a circle or an ellipse. Both of these functions, or I should be more specific and say relation, both of these relations, neither of them pass the vertical line test, so they don't count as functions, and therefore our techniques that we've developed thus far don't work with them. And there's all kinds of different types of curves that you could come up with that would not pass a vertical line test, but you would want to be able to do some sort of calculus-based analysis for. So to expand that, we're going to introduce what's known as a parametric set of equations. So the parametric set of equations really are two different functions based off of a third variable, generally t. And we allow t to be different values, and then we have a function for x, and then we have a function for y. Each of the functions for x and y would pass a vertical line test separately, although the function for x might pass more like a horizontal line test. But they are functions. And we can calculate our x and y values based off of input parameters for the value of t. If we graph points based off of a set of parametric equations, we create what's known as a plane curve. So let's take a look at generating a plane curve to help remind you exactly what this process is and what it looks like. So here I would like to sketch the graph described by the following parametric equations. So I have one parametric equation, x of t equals t minus 1, so that's a function for the x variable. And then I have y of t equals 2t plus 1. So that's a function in terms of the y variable. And then I have a restricted domain for the variable t. Now you always have to have some sort of domain for the variable t, and it's completely okay if that domain is just all real numbers. But you want to have some start and end point. So the start and end points could be inclusive or exclusive, or if it goes to infinity, that's fine as well. But let's take a look at how we could produce a graph from this. So what we do is we list out the values of t that we have, and for our purposes we'll list integers, but the calculator probably uses smaller increments, like going from -3 up to +2 by increments of 0.1 instead of increments of integer values. And the use of integers is really just easier for us mathematically, but also gives us fewer values that we need to compute with. So x of t is telling us the value of our x-coordinate for when the point occurs when t is equal to -3. So if I put -3 into the function x of t, it would be -3 minus 1, which is -4. If I put in -2, it would be -2 minus 1, which would be -3. And then -1 minus 1 is -2. Then I would have -1, 0, and 1. So these are all the x-coordinates of points that exist on this plane curve. Now to graph, we need both an x and a y coordinate. So the y coordinate we just calculate based off of the other function here. So if I plug in -3 into the function 2t plus 4, it would be 2 times -3 plus 4, which is -6 plus 4, or -2. Then if I put in -2, 2 times -2 is -4, plus 4 gives me 0. 2 times -1 is -2, plus 4 is 2. And then when I put in 0, that would give me 4. Plugging in t equals 1 would result in 6. And finally, 8. So now I have a set of x and y coordinate pairs. So for instance, the first coordinate set, which I'll call point A, would be the x-coordinate -4, -2. The second coordinate point, which I don't have to name, I'm just simply going to show you where they exist on the graph, but that would be at -3, 0. So let's put these on a standard graphing xy plane. So I'll do it like this. X goes from -4, so 1, 2, 3, 4, that's good. And really only up to +1, so that's as far as I need to go there. And then we go from -2 to 8, so I'd actually better be a little bit careful here. I'll do -2, +2, +4, +6, and +8, just so I have space for everything. As long as your scale is indicated, it's fine if you change the scale. All right, so the point A is at -4, -2. So -4, -2 is right there. So we'll go ahead and label that as point A. Point B is at -3, 0. So that's right there. Point C would be the next point when t is equal to -1. So -2, +2. There's point C. And then point D would be at -1, 4. So that's right there. And then 0, 6, we'll call that point E, and finally point F is at 1, 8. Now, normally I would draw this graph and continue on to infinity, but my scale stops when t gets to 2. So this ends here. So it's really just this line segment that I'm graphing here. And if you'll notice, this is making up a linear function. And it should make sense because each of the individual functions were linear, so that the resultant function is linear. Had one of them been quadratic, we probably would have seen something of a parabola in nature. And if both of them had been quadratic, it's possible that we would see a parabola, maybe we'd see a circle. It's hard to tell until we do a little bit more analysis. But certainly, if both are linear, it does make sense that we would end up with a line here. Now, your calculator can do these things as well. So let's take time to review how that would work. If we go into the mode settings, you'll find an option somewhere that reads function, parametric, sometimes it's just PAR, and then polar or just POL, and possibly SEQ for sequential. Some calculators don't have that. Doesn't matter. Function's probably what you're set so far. Parametric is what we're interested in. So highlight that and select it. Now when you press Y equals, that's going to take you into a new screen for plotting. All right, so first off, I have this statistics plot turned on. I'm going to turn that off so it doesn't give us any trouble. And you'll notice I have 1, 2, 3, 4, 5 different graphs I can produce right now. Each graph is determined by a set of functions, x1 of t and y1 of t. At the moment, I've got a little bit here, and I'm just going to erase those so that I'm starting fresh. Now, if I want to graph a parametric set of equations, I have to provide both an x and a y. So the x was t minus 1. And notice now when I press this button here, x, t, theta, n, just whatever your input variable is for the current mode of graphing that you're doing, it will choose the appropriate variable, but ultimately it doesn't really make a lot of difference. Then the y is 2t plus 4. And I need to go into my window settings because there's some additional settings here. There's a tmin, tmax, and tstep. All right, so these are your bounds on the variable t. So ours bounded from -3 to +2. The step is how many points you want to do between each value. So we did a step of integers, so we did a step point of 1. But by default, the calculator tends to do more points than we do, so let's set it to 0.1. That's usually pretty safe. You don't want to set it too high because even though that will produce a better looking graph, it will take longer to produce that graph. So it's sort of a trade-off. Xmin, Xmax, of course, these are the same values here for your standard graphing. So let's just set these to the standard graphing window of -10 to +10 on both the x and the y. And I'll set my scale. The scale on the y and the x is just how often to draw a tick mark. All right, so we graph and see exactly what we drew. So see that the line here is a segment, has a start and an end point. And that start and end point matches up to exactly what we had right here. Okay, let's try another example. We want to sketch the curve described by the parametric equations x of t equals t squared minus 3, y of t equals 2t plus 1, and t going from -2 to +3. So we start off with a table. We want the values of t, and we just need enough values that we can actually draw a decent sketch of our graph. X of t, I'm just going to take each t value and plug right into the function. So right now I'm working with this function right here, t squared minus 3. So -2 squared minus 3 would be 4 minus 3, which is 1. 1 squared minus 3, well, -1 squared, which would be 1 minus 3 is -2. 0 minus 3 is -3. 1 squared minus 3 is -2 again. 4 minus 3 is 1. And 9 minus 3 is 6. So there's all the values of x of t. And then y of t, if I plug in -2 to this function, all right, so now I'm working with this function here. Let's see, so that would be -2 plus 1, so -4 plus 1, which is -3. -2 plus 1, which is -1. 0 plus 1, which is 1. 2 times 1 plus 1, which is 3. 4 plus 1, which is 5. And 6 plus 1, which is 7. Okay? That gives us our points. And let me try my scale a little bit better this time. So looks like -3 to 6, -3 to 7. So I'll do something like this, I think. All right, so 1, 2, 3, 1, 2, 3, 4, 5, 6. That's fine. All right, so 1, -3, there's my first point. -2 on the x, -1 on the y, there's my second point. -3, 1, so -3 and then up 1, there we go. -2, +3, 1, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, and then 7, which would be about right there. So we can see here the shape of a parabola, but notice this parabola is definitely not going to pass a vertical line test. All right, it definitely passes through more than one point. So this does not represent a function, but that's okay. In terms of a parametric plane curve, it doesn't have to. We can represent these types of relations, no problem. Just to check it in the calculator, and as a reminder how this is done in the calculator, let's try that again. So if I go under y equals, clear out what I have so far for the x1 and y1, and put these functions in. So I had t squared minus 3, and 2t plus 1. Always want to check your window before you graph, because the value of t min and t max often changes from one problem to the next. All right, if we graph it, there's our curve, which you can definitely see as a shape of a parabola, but it's certainly got a stop and start point. One thing I'd like to mention, just so you see what happens with the t-step, if I change the t-step down to 1 and hit graph, notice I still get an approximate curve. It's just because I'm using fewer sample points along the curve, it looks a little more blocky, because what the calculator does is exactly what we're doing here, but every time it plots a point, it just simply plays connect the dots in order to plot one point and then the next, and then it connects those 2 points with a line. And it keeps doing that throughout. So the more sample points you use, the better graph you're going to get, but it's a trade-off in terms of the calculation time. Okay, one last one here. And we want to sketch the curve described by the following parametric equations. So x equals 4 cosine t, and y equals 4 sine t on the interval from 0 to 2 pi. Okay, so probably got our work cut out for us, but I think this is definitely doable. The first thing we have to decide on is how we want to split up the interval from 0 to 2 pi. We want to make sure we use enough points that we get a decent looking graph, but we don't want to use too many where it takes a long time to calculate. So let's split this up into, say, intervals of pi over 4. So we start with 0, the next interval value would be pi over 4, and then pi over 2, then 3 pi over 4, and pi. Okay, then we would have 5 pi over 4, then plus another pi over 4 would give me 3 pi over 2, then it would be 7 pi over 4, just trying to do these fractions in my head, and finally 2 pi. All right, so here's my range of values, and now I need to calculate x of t and y of t for each one of these. Okay, so let's see. 4 times the cosine of t. Well, cosine of 0 I know is 1. So 4 times 1 is 4. Sine of 0 is 0. So that's going to be at 0. Pi over 4, sine and cosine agree with one another. It's square root of 2 divided by 2. If I multiply 4 times the the square root of 2 over 2, I just get 2 times the square root of 2. So each of these are going to be 2 square root of 2. And then pi over 2 is another quadrantal angle. So cosine of pi over 2, that's where cosine is 0, and then sine is 1. So that would be 1 times 4, which is 4. 3 pi over 4, this is another time where sine and cosine agree at root 2 over 2. It's just this time cosine is going to be negative, so this will be negative 2 root 2 and positive 2 root 2. Then at pi, we're at another quadrantal angle. Cosine is negative 1, multiplying by 4, of course, and sine is 0. 5 pi over 4, we're down in quadrant 3, where both sine and cosine are negative, but it's going to be 2 root 2 for each of those values, but just both negative. 3 pi over 2 is another quadrantal, 0, negative 4. And then 2 root 2, negative 2 root 2. And finally, 4, 0 again. Okay, so let's take these points and plot them. All right, so, whoops. All right, so 1, 2, 3, 4. 1, 2, 3, 4. All right, so let's plot the easy ones. So we have 4, 0, 0, 4, negative 4, 0, 0, negative 4, and then we're back to 4, 0. All right, 2 root 2, what is this value? Let's use the calculator to estimate that. So that's like 2.8. All right, so it would be 2.8 and 2.8. Then negative 2.8 and positive 2.8. Negative 2.8 and negative 2.8. Then positive 2.8 and negative 2.8. All right, so I think you're probably seeing here a circle. Although, I mean, maybe my point isn't quite, I feel like that's further out than it needs to be. I'm not great at drawing circles, but I think you get the idea. There you go, that's fine. Okay, so there is our graph. And let's check that graph against what's in the calculator. So even though these aren't polynomial functions, we can still use them for x1 of t and y1 of t. If I just plug in the x of t was 4 cosine t, and y was 4 sine of t. All right, checking the window here. T min to t max, I'm now going from 0 to 2 pi. And I probably want to use more increments than pi over 4 to draw this circle. A lot of times if you do something like pi over, say, like 24, all right, I think that, yeah, results in about 0.1. That's usually a pretty good value to use. Let's just go from -5 to +5 on the x and y, just because we know the radius of this circle is 4. Now, before I press graph, one last thing that you want to make sure you check on when you are drawing these. I've defined theta min and theta max in terms of pi. I need to make sure I am in radian mode. It's fine to use degree mode, you would just need to go from 0 to 360 instead. But let's just switch over to radian mode so that we get the correct graph. All right, now it certainly looks more elliptical. The problem here is that there are more pixels in the horizontal direction of this window than there are in the vertical. And I've assigned the same distance per each tick mark. You know, there's 10 tick marks this way and 10 that way. So we're not going to get an accurate representation of the graph. We can correct that. There's a feature if you hit zoom, come down to where it says zoom square, and it will adjust the values of your windows so that you get something that is using square pixels on screen. So we can see that it is a circle here. Okay, one last thing before I call this quits. I'm going to go in and I'm going to change t-step to something much smaller. So I'm going to use like pi over, let's see, 24 doubled would be 48. Let's do pi over 96. Okay, and I'll hit graph. Okay, that was much slower. I do have a nicer circle, but that was much slower. Now here's the thing. The circle started here, and then it revolved this way around the axis. That's an important thing to think about here when you have parametrically defined curves. They have an inherent direction to them, okay? And it's good to actually indicate the direction of the curve with a set of arrows on the curve. When it comes to finding derivatives, the direction of the curve is actually really important because it tells you the direction that the derivative is moving as well. And in terms of physics applications, that is vitally important because objects moving certainly have a directional component to them. So one thing that if you don't mark it on your graphs, that's generally okay, but if you just think about it, just think about that there is a directional component to any of these. So for instance, this one, the first point that we drew was here, okay, I'll call that A. And then we went down through to the last point, which would have been B, C, D, E, F, it looks like, which would have been up here. So the direction of this curve is this way. And of the example before that, the direction of this curve was this direction. We saw the individual points moving there. So just kind of consider that. That will come back to play when we are talking about derivatives for these types of functions, and is a very important concept there.